Welcome back. In the previous lecture, we learned about position kits and bras and about some of the subtleties in proceeding from discrete to continuous variables. In this lecture, we introduce the position operator and illustrate some of its properties. So we continue with the exploration of a particle moving along a line that we identify with the x-axis. So there is position x equals 0, x1, x2, and many more positions along the x-axis. We have introduced a set of kits and bras for each point on the axis, and we have a completeness relation where the sum of all of these kit bras, which is now an integral over the variable x, is equal to 1. And we have an orthonormality relation which involves the Dirac delta function as discussed in the previous lecture. And then for a state kit, we will have a wave function. So the state kit will be expanded in these basic kits, one for each position x, and then there is a wave function psi of x, which is just a bracket between the bra for position x and the state kit, and that's the psi of x, the wave function. And then, of course, the normalization of the state kit and bra to unit length, that becomes the integral over x, and then we have the psi of x complex conjugate squared. Let me just quickly repeat where this comes from. So I will insert the expression for the bra. So that's this integral. However, it's the integral for the bra. So we have the psi of x complex conjugate and then the x bra. And then for the kit, we have this again, but now it's an integral over x prime psi of x prime. And so we now remember that when this bra meets this kit, we have the Dirac delta function integration. Then integrating over x prime turns this x prime into an x, and so we get the psi of x complex conjugate times the psi of x, and that gives us the absolute square psi of x. So this psi of x squared is the analog of psi of k squared, where earlier we summed over k in the discrete case and get 1 for that. And these were the probabilities for finding the case. So there is psi 1, psi 2, and so forth. Squared gives us a probability for case 1, case 2, and so forth. Now we have the psi of x squared. And so if we now talk about a probability, it cannot be that the psi of x squared itself is a probability. Rather, what corresponds to this sum is the psi of x squared times the dx. Or more precisely, if we think of this psi of x squared to be some function which by its nature is positive, so here we have the psi of x squared. And the integral, which is the area under this curve, is 1. So that's the probability 1 for finding the particle somewhere. However, if we look at a finite interval, just between x1 and x2, we have this area, which I am now kind of picking out by writing an integral from x1 to x2, dx psi of x squared, and that will be the probability of finding the particle in the interval where x is between x1 and x2. So in these integrals where we integrate from minus infinity to infinity, usually we wouldn't write these limits because we just integrate over all x. Then that's the total area under the graph of psi of x. But for a finite interval like here, it's the area between x and x2 under the graph of psi of x squared. And that has the meaning of the probability of finding the particle in this interval, which is just like this expression for the discrete case, but now we have the continuous case. So the psi of x squared is not a probability. The dx times psi squared that we meet here, that's closer analog of the psi of k squared for the discrete case. So this is a probability element. We add up all these probability elements, we get the total probability of 1. We add up all the probability elements that refer to the range between x1 and x2, we get the probability of finding the particle in this interval. And so the psi of x squared itself is not a probability, but a probability density. So since dx, say if this is measured in centimeters, would be a length, and so this would be a probability per centimeter or probability per unit length for the psi of x squared. You multiply with the dx, you get a probability element, a small contribution to the probability. You have to add up all the contributions of a finite range to get a finite probability. So we have the wave function and the squared wave function multiplied with the differential dx is the probability element for the vicinity of x, probability of finding the particle there. So if we have a lot of particles all prepared such that they are described by the same one wave function psi of x, and then we look for the particles, so sometimes we find it here, sometimes we find it there, sometimes we find it there, and the probability for finding it in the vicinity of a particular x is given by the psi of x squared. So now imagine that we have measured many such particles. I have a whole list of these x values and distributed in accordance with this probability distribution. Then we can ask, what's the average value of x? What's the mean value of x? So the mean value of x will be, well, the sum of the x is weighted with this probability for each x. And so we have the psi of x squared multiplied by x for the mean value of x. And we can also ask, what's the mean value of x squared? Well, here we just add up the values of the squared x's weighted by the probability that goes with each vicinity, and so forth, right? Now, if we want to make contact with the formalism that we had for other situations, we would like to read this as the expectation value of an operator that we associate with position. And this would then be the expectation value of the square of this operator. So here x is the position operator, and this is the square of the position operator. So our challenge is now to find the x such that these equations are correct as we have written them. Now let's see. And before I proceed, I should of course mention that this x is not the x that we had as one of the Pauli operators x, y, z for the qubits. This is the x same letter is used here for the position operator. It's a bit unfortunate that this x is the same letter as the x, y, z that we had before, but there is just a finite number of letters in the alphabet, and sooner or later we have to use some of the letters with more than one meaning. But hopefully in the context it will be clear what we are talking about. So let's look at this x average value and put in where the psi of x comes from. So there's the integral over x, and then the psi of x is the wave function squared, which I'm now writing like this. So this is the complex conjugate wave function, and this is the wave function itself, and the product is the square of the wave functions. And now you have the state bra on the left and the state ket on the right. And in between you have an integral over x. Yes, there is the ket bra for the position operator, and there's the number x from here. So there's the number x, the ket x, the bra x, number x, ket x, bra x, and then there is the state bra, and then there is the state ket. And so this is clearly the expected value of this operator. So it's an operator that I'm now identifying with this position operator. And so we find that from this statement that the x operator should be equal to this. But that's also the natural thing, okay? So we have the x ket bra that refers to the position x, or actually to the vicinity of x together with the dx, and then there's the value of x. So, but now let's see, if with this definition we look at the expected value of x squared, whether it agrees with this expression. So let's do that in the next line. So I'm now looking at the expected value of x squared. So that's the bra for the state, the operator x squared, the ket for the state. Okay, so the bra for the state, we integrate over x, ket x, number x, bra x. That's one of these x factors. Integral x prime, ket x prime, number x prime, bra x prime. That's the second one of these x factors. It's just that the integration variable is now called x prime, so we don't confuse the two integrations. And then there is the ket for the state. So once more, we have the bracket of an x bra with an x prime ket, and that's equal to the delta function. And so we can then integrate over x prime, and that turns this x prime and this x prime into an x, after which we have an integral over x all by itself. The state bra together with the position ket, that's the wave function complex conjugate. Then we have an x, and this x prime becomes a second x. There's an x squared. And then we have the state bra x prime, but because of the delta function, this has become an x, together with the position bra for x and the state ket, and that's the wave function at x. And yes, the product of complex conjugate wave function is the square of the wave function, and then there is the x squared from here. And so this expression is equal to what we have called the mean value of x squared above. And more generally than that, we can talk about functions of the position operator, which in very close analogy to what we did in the discrete case before, is just this integral now evaluated, that where the number is the function at the value of x, at the position x. So this is the function of the operator, this is the function of the variable x, and we integrate with the ket bra for the position x, ket bra for the position x, the number f of x, and this will be the expression for an operator function of the position operator, expressed in terms of the ingredients that go with the position ket, the position bra, the function value at the position, summed over all x's, which is done by an integration. Alright, so before we move on, let's look at an example. Let's consider a situation where the wave function has a simple structure, which I will write down, square root of a parameter kappa, which is positive, exponential function of negative kappa times the absolute value of x. So first thing that we want to verify is the normalization. So I integrate over x. This is from negative infinity to infinity as always. And then we have to square this, so we have the kappa, and then we have to e to minus 2 kappa absolute value of x. Now for the absolute value of x, we go for negative x's or positive x's. In one case it's x itself, the other case is negative x. So it will be easier if we just integrate from 0 to infinity dx, and then there's kappa e to the minus 2 kappa x. So that would be for the positive values, but if I have the negative values, then it's the same integral again. So there's a factor of 2 for the overall value, which is basically saying that the contribution we get from positive x's and the contribution that we get from negative x's is the same. So I just calculate the contribution for the positive x's and then multiply this by 2 to account for the negative x's. But this is an elementary integral, and we see that the value is 1. Then now, what about expectation values of x? So what about the expectation value of x and x squared and x cubed and so forth? Now, rather than calculating them one by one, I will look at the expectation value of e to the I kx, and then recognize that by expanding the exponential function, this is the expectation value of the identity, which is 1. Then it is IK times the expectation value of x plus half of IK squared, the expectation value of x squared, plus 1/6 IK cubed, the expectation value of x cubed, and so forth. So by evaluating this expectation value and then expanding in powers of k, we can read off the expectation value for x, x squared, x cubed, and so forth. So let's do that. So what is this expectation value of e to the I kx? Well, that would be the integral over x, the wave function squared, e to the I k number x. Right, so here I'm just making use of the fact that this e to the I kx, it can be written in terms of the kets and bras that we have for the position x, just as we discussed a few minutes ago, and then looking at the expectation value will give us the wave function squared and then this function of x. And so this is, again, it's the integral from minus infinity to infinity dx. There is the kappa, the square of the wave function, e to the minus 2 kappa absolute value of x, e to the I kx. And now, again, I will look at the contribution of the positive x values, dx kappa e to the minus 2 kappa x, e to the I kx. And then I look at the contribution from the negative x values, where the e to the ik comes with a negative value for x. So I account for that by adding in e to the negative ikx. So this is the term that we get for the positive axis, and this is the term that we get for the negative axis, but here parameterized with positive values of x. So this is the same thing. So, and these integrals are elementary. The first one is kappa divided by 2 kappa minus ik, and the second one is kappa divided by 2 kappa plus ik. Alright, so we combine this into one expression, then it will be 2 kappa and 2 kappa, 2 kappa, 4 kappa squared, 2 kappa squared, and here we have 2 kappa squared plus k squared. Right, by just combining the two fractions into one. And I'm going to rewrite this a little bit by dividing the numerator and the denominator by the 2 kappa squared. So it will be 1 plus k divided by 2 kappa squared. Where we recognize that this is easily expanded in powers of k by just seeing here the result of summing a geometric series. So this is equal to 1 minus k divided by 2 kappa squared plus k divided by 2 kappa to the fourth, and so forth. So what we have to do now is compare this expression with this expression. So both are equal to the expectation value of e to the ikx operator. Here we have worked it out for this particular wave function. Here we have a general expression that would be valid for all kinds of wave functions. Anyway, for this particular wave function, there is no term that involves a single k. So for this particular wave function, the expectation value of x is 0. Well, if we go back here, we see that this squared wave function is an even function of x. Positive x and negative x contribute the same way. So it's not a surprise that the expectation value of x is 0. And for the same reason, the expectation value of x cubed is 0. And in fact, the expectation value of any odd power of x will be 0, because here we only have even powers of the parameter k. And so if we look at odd powers of the parameter k that appear here, they go with odd powers of x, because it's the product kx that defines everything. And so there will be no terms here that involve odd powers of k. So all the terms here that go with odd powers of k have to be 0. So all the expectation values of x with odd powers of k have to be 0. In particular, expectation value of x is 0, expectation value of x cubed is 0. What about expectation value of x squared? Okay, so here we have to look at the term that goes with k squared. Over here it is, because of the I squared, it's negative k squared half, expectation value of x squared, and here we have k squared divided by 4 kappa squared. So this has to be equal to 2, 1 divided by 2 kappa squared. So that if I divide by another 2, I get 4 kappa squared, and I have the k squared here. And for x to the fourth, well, we read off there. Okay, I haven't written the term, but if I just continue here, then the next term is 1 over 4 factorial 24 ik to the fourth and x to the fourth. So that would be the next term here. So it's k to the fourth, I to the fourth is 1, k to the fourth, k to the fourth here. It's 1 divided by 24. So I have to multiply the the 2k to the fourth in the denominator by a 24 in the numerator. And so this is 3 divided by 2 kappa to the fourth. And we can just read off all the other expectation values of powers of k in the same way, but I will stop here with this exercise. In summary, we now have the position operator that goes with the position kets and bras. In the next lecture, we deal with its partner, the momentum operator.